Hi, everyone, and welcome back. I'm Dan Fullerton, and today I'm pleased to talk to you about one of my favorite topics in all of AP Physics C, Gauss's law. Our goals are going to be to understand the relationship between electric field and electric flux to calculate the flux of an electric field through a surface, state Gauss's law in integral form and apply it to relate flux and electric charge for a specified surface, use Gauss's law to determine the electric field for a plane, spherical, or cylindrically symmetric charge distribution, and to apply Gauss's law to determine the charge density or total charge on a surface in terms of the electric field near that surface. Now, as we get into Gauss's law, it's all about electric flux. So what is electric flux? Well, really, electric flux is the amount of electric field penetrating a surface. For example, if we want to think of wind as electric field for the moment, going through a surface, if I have an index card like this, as I blow on it, I have a lot of field, a lot of electric field going through it. There is a lot of flux through the surface. If I turn it perpendicular, however, not nearly as much is going through the surface. I have much less flux. That's what we're talking about when we talk about electric flux, the amount of electric field that penetrates a surface. The symbol for it is the Greek letter phi. And if we talk about an open surface like this, the way we define electric flux is by talking about the electric field going through that. And we're also going to define a little tiny bit of area on that surface, a differential of area dA. And the dA vector is going to be that area with the direction that is perpendicular to that surface. So if we wanted to define the little bit of flux going through there, we could write that d phi, the differential of flux, is equal to the electric field dotted with dA. Or that's going to be E times dA times the cosine of the angle between them, theta. Therefore, the total flux phi is going to be the integral of d phi, or the integral over that entire area of E dot dA. So when we're talking about electric flux, especially through an open surface, that's what we're talking about. However, not all surfaces are open. Sometimes you have closed surfaces. Think of a balloon that's blown up, for example. When we have a closed surface, how do we define flux? Well, normals to closed surfaces point from the inside to the outside, and we define it the same way. We take a look at the total surface. Closed, open, doesn't matter, and we look at the total amount of flux going through it. If the flux is going from the inside to the outside, we call that a positive flux. If it's going from the outside to the inside, that is a negative flux. So, normals to closed surfaces point from the inside to the outside when we're talking about these. If there's more flux from the outside to the inside than inside to outside, you have a negative total flux, and vice versa for a positive total flux. The way we would write this is that the total flux phi is going to be the integral of d phi over that entire closed surface, which we write as the integral over a closed surface. There's a sign for integral over a closed surface of E dot dA. All right, so what's this have to do with Gauss's law? Well, what we're going to do is consider a point charge with charge plus q inside a spherical shell of radius r. The electric field due to plus q is pointing out, that's shown there in green, and we want to determine the flux through this blue sphere that's surrounding our point charge. We have to imagine it in 3 dimensions. So as we do this, we're going to start off by finding the differential of flux, the little bit. So d phi through some little bit of surface area, dA here on the sphere, is going to be E dot dA, which is, as we said, E dA cosine theta. But here, take a look. The angle between the electric field and dA anywhere on that surface, because it's symmetric, everything's radial, is always going to be 0. So if theta is always equal to 0, then the cosine of theta is always going to be equal to cosine 0, which is 1. So we get that d phi is just equal to E dA. So let's find the total flux then. The total flux, phi, is going to be the integral of d phi, or that's the integral over our closed surface now of E dA. But take a look. The electric field should be constant at all points on here. It doesn't vary over that area. We can pull that out of the integral sign. So that's equal to E integral over the closed surface of dA. And the integral over the closed surface, dA, is just going to be that total area. So that's equal to EA. Now, for our case here, the total area that we're dealing with, the area of a sphere, is 4 pi r squared. So because A equals 4 pi r squared, we can then say that our total flux, phi, is equal to 4 pi r squared times E. Hang in there, we're almost there. We also know the electric field due to that point charge, though. The electric field due to a point charge, we learned previously, is going to be Q over 4 pi epsilon naught r squared. So then our total flux is 4 pi r squared times E, but E is Q over 4 pi epsilon naught r squared. We've got some pretty slick cancellations coming up here. 4 pi, r squared. Therefore, the total flux is Q over epsilon naught. So putting this all together, total flux phi is equal to the integral over the closed surface of E dot dA, which is equal to the total charge enclosed by that surface divided by epsilon naught. That's Gauss's law. Now, as we talk about that, Gauss's law is useful for finding the electric field due to charge distributions for cases of spherical symmetry, cylindrical symmetry, and planar symmetry. It's always true, but it's not always all that useful. So let's take a look at how we could apply it. Let's find the electric field due to a thin, hollow shell of charge with charge Q. Let's find the electric field both inside and outside the shell. And the way we're going to do that is we're going to start by choosing what we call a Gaussian surface as a sphere, first inside the shell of charge and then outside. And by symmetry, we know that the electric field at all points on that sphere, on our Gaussian sphere, must be the same, and it must point radially in or out. So let's start on the inside. Let's define a Gaussian surface inside our blue shell of charge. Our Gaussian surface is this imaginary sphere inside with radius Ri that's centered inside of it. If our actual radius to our shell of charge is capital R, we could then say that the integral over the closed surface of E dot dA must be equal to the total charge enclosed divided by epsilon naught. Well, when we look at this then, E dot dA is just going to be, well, E is going to be constant. That's going to come out of the integral sign, and the integral over the closed surface of dA is just A. So really what we get on the left-hand side is EA, and our area is 4 pi r squared again. So 4 pi r squared E equals Q enclosed over epsilon naught. Therefore, if we solve for the electric field, E is just going to be Q enclosed over 4 pi epsilon naught r squared. But what's the charge enclosed by Ri, by our Gaussian surface here? Well, it's got to be 0. There's no charge enclosed. The charge is only on the shell. Therefore, the electric field inside equals 0. So this is for inside the shell. Let's try the same thing outside the shell. Now we'll make a different Gaussian surface. Let's call this RO for R outside. We want to know the electric field somewhere on this Gaussian sphere due to this hollow shell of charge, Q. Again, the integral over the closed surface of E dot dA equals Q enclosed over epsilon naught. And once again, 4 pi r squared times the electric field must be Q enclosed over epsilon naught. Therefore, the electric field must be Q enclosed over 4 pi epsilon naught r squared. But our charge enclosed now isn't 0, it's capital Q. Therefore, our electric field outside must be the charge that's on our shell, capital Q, divided by 4 pi epsilon naught r squared. The same answer is if all of the charge Q was placed at a point in the center of the sphere. So from the perspective, once you're outside the shell, it doesn't matter if it's a shell or if it's a point charge or where the shell is. It only matters the total amount of charge in there once you have that symmetry. If we wanted to draw a quick graph of what the electric field would look like, there's our electric field versus distance, R and E. We'd probably have something that looks kind of like this. Inside, up to the point where we are at capital R, the radius of our shell, we have no electric field. And after that, we have something that is proportional to 1 over r squared. So there's our first application of Gauss's law, using it to find the electric field due to a thin, hollow shell, both inside and outside the shell. Now let's take a look at a second application where we want to find the electric field due to an infinite plane. We'll consider an infinite plane of uniform charge density sigma with total charge Q over A. Find the electric field due to the plane. Well, in this case, we're going to choose a Gaussian surface as a cylinder. By symmetry, then, the electric field at all points on the cylinder must point perpendicular to the plane through the caps of the cylinder. What's that mean? Well, let's see what we can draw here. There's our cylinder as it intersects the plane, and we'll continue our cylinder up. And let's make it go the same distance below the plane as well. Okay, we will call the area of the end caps capital A, and we'll say the distance from the plane itself to the caps is D. Now, by symmetry, since it's an infinite plane of charge, we should be able to see that we're not going to have any horizontal component of electric field. It's only going to be pointing up or down, perpendicular to the plane. That's where the symmetry is going to help us out here. So let's go to Gauss's law, the integral over the closed surface of E dot dA equals the enclosed charge divided by epsilon naught. Now, to help us out here, we can define sigma as equal to Q over A, a surface charge density, so that Q must be sigma times the area. Now, as we look at the left-hand side, that's all equal to the total flux. And I'm going to break the flux up into a couple different pieces. The flux through the top cap, the flux through the bottom cap, and the flux through the cylinder sides, which we know is going to end up being 0. So we have the flux, electric flux through the top, plus the electric flux through the bottom, plus the flux through the sides, which I'll call the electric flux, well, E, how about R? And that all must be equal to Q enclosed over epsilon naught, which in this case, Q enclosed is just going to be sigma A over epsilon naught, where A is our area of our cylinder cap. And by symmetry, of course, we can say that the flux through the sides is going to be 0. Therefore, the flux through the top plus the flux through the bottom must be equal to sigma A over epsilon naught. And the flux through the top is just going to be the electric field times A because everything's perpendicular. So we have EA through the top. We have EA through the bottom. So that's 2EA must be equal to sigma A over epsilon naught. Or solving for the electric field is sigma A over 2 sigma naught A, or sigma over 2 epsilon 0. That should sound pretty familiar if you look at some of our work from the continuous charge distributions in our previous videos. And if we wanted to make a graph of that, here's our electric field, here's our distance from that infinite plane. We would have a nice constant sigma over 2 epsilon naught. No dependence whatsoever from the distance, no dependence on the distance from the plane. Same thing we saw previously. That's good. We like when things are consistent. The electric field due to two parallel plates. And as we're going to talk about these charged plates, or parallel planes even, we're going to use our result from the last problem. What we're going to do is we're going to find the electric field surrounding and in between these two oppositely charged parallel planes or plates by finding the electric field due to an infinite plane on top and the infinite plane on bottom, and then just adding them together. So we'll start with the top one. I'll do that in this bright pink to go with the red so that it shows up pretty well. We know that if this is a positive sigma, positive surface charge density, there must be an electric field pointing away from it, and its strength must be sigma over 2 epsilon naught. And on the other side, it must point away to sigma over 2 epsilon naught, and no dependence on distance, so it continues sigma over 2 epsilon naught. Now, due to the bottom plane, we have a negative surface charge density. So the electric field is going to point toward it. So here we have sigma over 2 epsilon naught pointing toward it, sigma over 2 epsilon naught, and sigma over 2 epsilon naught, all pointing toward the blue plane because it's got the negative surface charge density. So what happens when we add those together? Over here on the right-hand side, we've got sigma over 2 epsilon naught up, sigma over 2 epsilon naught down. The electric field there is 0. In between, we have sigma over 2 epsilon naught plus sigma over 2 epsilon naught. So the electric field between them is equal to sigma over epsilon naught. And down below, we have 1 down, 1 up, so 0 again. So the electric field between these parallel plates or parallel planes is sigma over epsilon naught. Now, as long as you're not near the edges of the plane, that's pretty good. If it's an infinite plane, perfectly accurate, but since those don't really exist, you have to understand that if you get too close to the edges, it doesn't work anymore. But anywhere between these two, as long as you're not near the edges, the electric field is constant, sigma over epsilon naught. Let's try just one more. The electric field due to an infinite line charge with charge density lambda. And we want to go some distance r away from that line charge and figure out what the electric field is at that point. Well, now I'm going to come back to cylindrical symmetry. To help me solve this one, I'm going to pick a Gaussian surface that's a cylinder centered around the line of charge. So there's one end of my cylinder. There's another end of my cylinder. And we'll make sure that R is right on the edge of the cylinder. So there's our imaginary Gaussian surface to help us solve this. Now, it's pretty easy to see by symmetry again that we're not going to have any net electric field through the caps of the cylinder. It all has to be pointing radially out through the cylinder. That's going to make this much more helpful, and where Gauss's law becomes practically useful is when you have these conditions of symmetry. So, we'll start again. Integral over the closed surface of E dot dA equals the enclosed charge divided by epsilon naught. we'll call the flux through the left-hand side phi L, the flux through the right-hand side phi R, and the flux through the cylinder part phi cylinder. So the left-hand side becomes the flux through the left plus the flux through the right plus the flux through the cylinder must equal the enclosed charge divided by epsilon naught. And once again, we can make that symmetry argument that the flux through the left and the flux through the right must cancel out because that's an infinite line charge. So we're going to be left with the flux through the cylinder equal to the enclosed charge divided by epsilon naught, divided by epsilon 0. Now, what about that flux through the cylinder? This implies then the flux through the cylinder. How can we figure that out? Well, we can think about it, the flux through the cylinder. Imagine we took that cylinder as a circle and we cut it so that we could lay it all flat. If we did that, well, what are the dimensions of it going to be? If it started off like this, it's got a circumference for one of the lengths. So 2 pi r is one of our dimensions. We also have the length of our cylinder, L, is another dimension, and we have, of course, the electric field going through it since this is our flux, E. Therefore, we can write that 2 pi RL E must equal Q enclosed over epsilon 0. Now we come to this surface charge density again. Or pardon me, this linear charge density. Lambda is our total charge divided by L, so that the charge enclosed must be lambda L. So 2 pi capital R capital L times the electric field must equal lambda L over epsilon naught. Or solving for the electric field again, electric field is lambda L over epsilon naught divided by 2 pi RL. We've got a couple cancellations. Our L's cancel out. And I'm left with the electric field equal to lambda over 2 pi epsilon naught R. The same answer is that what we reached when we were talking about the continuous charge distributions. And of course they should match up. But look how much easier this is if you apply Gauss's law. Very straightforward, very easy integration. In all honesty, we didn't really do any of the actual integration. We used our common sense to understand what the integral was asking for in order to solve for the electric field. So, hopefully that gets you a great start with Gauss's law. If you're looking for more information or need more help, check out aplusphysics.com. Thanks so much and make it a great day.